One of the strangest formulas that comes up in introductory statistics is the sample variance formula. And in particular, the sample variance formula is strange because it seems like a very natural thing to do, right? We take the summation of our data minus the sample average of our data, we square that, we add all those things up. But then the weirdness comes because instead of dividing by n, which would be the natural thing to do in this situation, we divide by n-1. And this is a formula that generates a lot of confusion, a lot of questions, and it all centers on why are we dividing by n-1? And so when we're calculating the sample variance, it's very possible for us to view this as an estimator of the population variance. That's sort of a natural way of framing this. And the main justification for dividing by n-1, rather than dividing by n or something else, is that if we divide by n-1, the estimator of the sample variance is unbiased for the population variance. And this is typically a desirable property. So let's explore exactly what we mean here. So the sample variance is given by this expression here, right? So we sum up all of our data points and subtract off their mean, right? So the sum of xi minus x bar squared, we add those all up, and then we divide by n-1. And it's this division by n-1 that is typically the point of confusion. Now, to sort of draw the parallel here, the population has a variance that's given by the expected value of x minus its mean squared, and then it's taking that in expectation. And so in a lot of ways, right, we can think about this internal term here as sort of being connected to what we're adding up, right? So we take x minus its mean, and then you square it. Here we're taking x minus its mean, and then you square it. But instead of taking the average of this term, right, which would involve us dividing by n, instead we take this division by n-1. And so the question is, well, why are we doing that? Okay. And the reason that we're going to do that is because if you form s squared this way, then it's going to be unbiased for the population variance. And so by that, we mean that the expected value of s squared is equal to sigma squared, where sigma squared is the population variance. And so this is a desirable property, and it can be very useful in certain settings. However, it's worth sort of pulling at this a little bit more, right? Because is this actually the best choice? Now, when we're assessing estimators, there's the bias that we care about, but there's also the variance that we care about. And the way that we take bias and variance together into account is through the MSE, right? So the MSE of the sample variance is something that we could take a look at. Now, unfortunately, the MSE is going to be a lot harder to calculate than the biases itself. And so instead of tackling this problem in general, we're going to be thinking about this in one specific case, right? But the general idea is going to be that rather than thinking about the lowest bias estimator, what if we thought about the estimator that has the lowest MSE? And so the MSE is going to be capturing both the bias but also the variance. If we take the lowest MSE, then in some sense we're getting the best possible estimator. So if we think about just normal populations, right? So our data are being drawn independently from some normal distribution, then it's possible to show that the MSE of our sample variance estimator is 2 divided by n-1 times sigma to the power of 4. And in this case, when we're thinking about sigma here, right, sigma here, sigma squared is going to be given, or gives us the population variance, right? So we have that sigma squared is the variance, right? And so then sigma to the power of 4 is going to be the variance squared, right? And so the MSE is somehow related to the variance here, and in particular, it's 2 divided by n-1 times by the variance squared, okay? But we could ask ourselves, well, what happens if we take a different estimator, right? And so if we think about instead still doing our summation from I equals 1 to n of xi minus x bar squared, right? So that part is very natural. But what if instead of dividing by n-1, we divide by n? So we take 1 over n times by this, okay? And if we do this, then what we can show is that, again, in this normal population, the MSE of the sample variance is going to be 2 times n-1 divided by n squared times by sigma to the power of 4. So it's a similar looking MSE here, but it's slightly different, right? We have 2 times n-1 in the numerator and n squared in the denominator, rather than 2 over n-1. Okay. Now we could take this one step further, and if instead of doing the natural thing of dividing by n, we divide by n plus 1, we get an additional estimator here. So if we do the exact same expression, right, but instead of dividing by n, we divide by n plus 1. So we have 1 over n plus 1, the sum from I equals 1 to n of xi minus x bar squared. This estimator is going to have an MSE of 2 divided by n plus 1 times by sigma to the power of 4. Okay, and so we have these three sort of competing estimators here. And in terms of the MSE, the best estimator is always the one with the lowest MSE. And it turns out that both 2 and 3 are smaller than 1 for any sample size that we can plug in. Right? We plug in any n greater than 1 here, and we're going to get that 2 and 3 are both smaller than 1, which means that the MSE dividing by n or dividing by n plus 1 is going to be smaller than the MSE dividing by n minus 1. So in particular, in this setting, we're going to be given the smallest MSE by dividing by n plus 1. Of all of the things you could divide by, n plus 1 is the best thing to possibly divide by. Now, I'll add the caveat that this is only for normal populations, right? If we don't have normally distributed variables, then you're going to have to look sort of for other justifications here. But the point that I'm making is that dividing by n plus 1 actually gives you a better estimator in a case that we oftentimes care about, rather than dividing by n minus 1. It feels just as arbitrary, but here we could justify this as being the lowest MSE estimator, the best estimator, rather than the unbiased estimator. Right? And so it's sort of this question of, should we really be dividing by n minus 1? So the unbiased variance estimator is not going to give us the lowest MSE in general. Okay, so just as a general rule, it's not actually going to be our best estimator for variance. And so with that, why do we still use this, right? And so even though it's suboptimal in terms of MSE, it might still sometimes be worth using the sample variance. The first reason is that unbiasedness is oftentimes very desirable. There are cases where we need to use the variance, where knowing that it's unbiased really is actually sort of a benefit. Now, it's also important to note that historically, as well as into modern times, this is the estimator that everyone uses, right? Basically, everyone is going to be dividing by n minus 1. And so there's good reason that every time that we're calculating a sample variance, that everyone does it in the same way, right? Because if you're reading someone else's work and they report the sample variance and they've divided by n minus 1, and then someone else has divided by n plus 1, it's going to be very confusing to try to pull all of those results together and sort of synthesize the knowledge that we're gaining there, right? And so it's useful to adopt a convention. This is the convention that has been adopted for historical reasons, but it's quite useful to continue using that for those reasons today. Another point, and this is sort of an important subtle point, but the optimal MSE is going to depend on the population distribution. So all of those MSEs that we just saw, they assumed normality, and then they worked out what the MSE was. The unbiasedness of the estimator does not. It's unbiased no matter what happens with the population distribution. And so because of that, this sample variance is going to be useful across every population distribution. It's always going to be unbiased, whereas the optimal term for the MSE might not be the same for every different population distribution. Okay. Despite all of this, it is worth keeping in mind that the sample variance estimator is not the only possible sample variance estimator, and there's actually good reason in certain settings where one might be more justified than the other, right? It might be situations that come up where it really would be better to divide by something other than n minus 1. And just because someone's doing that does not necessarily mean that they're making a bad choice. One final point to note is that in the end, if you have a reasonably large sample, whether you're dividing by n, or you're dividing by n minus 1, or you're dividing by n plus 1, it effectively all works out to be the same. So really, these are only going to make differences in small samples anyways. But that's why we use it. We use the sample variance estimator that we do, so that it's an unbiased estimator. There's still good reason to do this today, but it is important to note it's probably not going to be the best estimator in terms of the MSE of the estimators.